Determine whether the relationship represents y as a function of x. For example A, we have a relationship between x and y that's listed here. 5x plus 2y equals 10. You can see a picture of this relationship below, and it looks like it's a line. When we're trying to determine whether a relationship is a function, we want to make sure that for any x value that we choose, there's exactly one output y value. Suppose I pick another x value here. I'm getting exactly one output value. So looking at the graph, we think that this is a function. The other thing that we can do is try to solve for y. If we can get y by itself on one side of the equation and x on the other side without options for that, we can say that that is a function. So let's take our given relationship here. I'm going to start by subtracting 5x from both sides. I want to move everything away from y. And then I will divide both sides by 2. So we get y is equal to negative 5 halves x plus 5. That is in fact a line. We can see that the slope here is negative 5 halves. That matches with what we're seeing in the picture. And we can see that the y-intercept is 5. Again, that's matching with what we see in the picture. So this is in fact a function. And we can see that from the picture, and we can also see that because we're able to solve for y on one side of the equation and get a single option for our x values. Looking at example B, if I think about just looking at the graph, if I pick a particular x value and I plug it into the function, I want to make sure that I'm only getting one output value. And it looks like that's the case. Let's take the relationship that's given here and let's try to solve for y. Let's subtract 3x squared from both sides. And then we get that y is equal to negative 3x squared plus 14. This matches up with the graph. It's a parabola that's facing upside down. I know it's a parabola because it has an x squared here. And then because it's got a negative 3 multiplied in the front, that means that it's facing upside down. And then the plus 14 that's on the end, that's shifting the whole thing up. So it looks like up here, maybe we're at 14. So because I'm able to solve this to be y equals, then I can say that this is in fact a function. Here's an example that's not going to be a function. We can look at the picture and see if I pick a particular input x value, I have two different options for a y value. So just based on the picture, this is not going to be a function. Let's see what happens when we try to solve for y. I'll start by subtracting x squared from both sides. And then I will take the square root of both sides. When I take the square root, I have to remember that there are two options. There's either a plus or a minus. So I'm going to end up with two different possibilities for my input and my output. When I think about the positive square root, that's going to give me all the values up here that are above the x-axis. And when I think of the negative square root, that's going to give me all the values down below here that are below the x-axis. So looking at the way that I've rearranged this to solve for y, I can see that this isn't going to be a function because I'm ending up with these options here of plus or minus. And for our final example, we're looking at 2xy equals 1. Now looking at this function as the graph, if I have one input, I can see that there's one output. For every input, I can find one output. Let's try to solve this and see what happens. Solve for y. 2xy equals 1. We can divide both sides by 2 times x, and we end up with y equals 1 over 2x. We can see that there's a single value that we're getting for each of our y's, single input for our x's, and so this is in fact a function. But we also just want to note, because it's kind of based on some things we've done in the past, we have to say that x cannot be equal to 0. Because that would put 0 in the denominator. And we can see that in the graph. We can see that we're getting this horizontal asymptote here at the y-axis because we're not allowed to plug a 0 in for x.